Hello everyone, thanks for attending my talk, Crushing Your Way to Medium Integrity, Exploiting the PDB Parser for Privilege Escalation. My name is Gal, and in the past few years I've been doing security research for Palo Alto Networks, mainly in the fields of fuzzing, vulnerabilities, exploits, and mitigations. I've also been awarded as Microsoft MSRC Most Valuable Security Researcher for the past 3 years in a row for discovering over 40 different vulnerabilities in Microsoft products. Today in this talk, we'll discuss one of the more interesting bugs I discovered last year and how it can be exploited. And I'd start by explaining what are PDB files, how I discovered vulnerabilities in Microsoft's PDB Parser, followed by the different attack surface into that parser, an exploit, and a demo. So PDB files store debugging information, also known as symbols, about a Windows executable program. Those are stored on top of these files rather than the executable files themselves. They contain things like function names, globals, type information, and so on, and are created from source files during the build process. Then they're used by debuggers to display the debugging information in a meaningful way throughout the debugging session. Here is an example of using WinDBG to load the PDB file of Notepad and then use the X command to simply dump all symbols from it. The PDB file format itself is a proprietary file format invented by Microsoft. It is binary and is built on top of another file format called MSF, which is a simple file system-like format that allows to store different streams onto a single file. While there's no public RFC document by Microsoft for that format, they open source the code for producing PDB files, so non-Microsoft compilers can produce them too. The parser for PDB files is implemented in DbgHelp.dll, which is a shared library that's shipped by Windows by default on every Windows installation. And it provides an API to debug a process, load PDB files, extract symbols data, and so on. So the initial goal for this project was trying to identify vulnerabilities in the PDB parsing code. And the way I decided to do so is to use fuzzing. And my fuzzing setup was quite straightforward. I started by collecting a corpus or an initial set of valid PDB files from several sources. Then I coded my test harness program, which is a program that simply loads a single PDB file from disk and parse it using the DbgHelp SimLoad module API. Then I used the very well-known open source fuzzer called WinAFL to do the actual fuzzing. And WinAFL is a mutation-based fuzzer, and the basic workflow for mutation-based fuzzers is that they select a single input from the corpus. They then create a new test case by mutating that sample, doing things like bit flips and byte flips. They run the test case through the test harness and check if it crashed, and then repeats that process infinitely. There are many optimizations WinAFL does on that basic workflow, but I won't go into details about it right now because WinAFL is very well documented, and this is not a fuzzing talk. But what I want you to take away from here, if you haven't done fuzzing yourself, is that setting this up is very simple. And in a couple of hours, collecting a corpus and writing the test harness in the way WinAFL expects, you can bootstrap your fuzzing campaign, and this requires no much knowledge of the PDB file format at that stage. And here is WinAFL's dashboard from fuzzing the PDB parser on a single core for 3 days. And as you can see, it discovered over 200 different crashes in that fuzzer, in that parser. So that was a pretty good starting point for that project. And then I decided to look for an attack surface to exploit those bugs. And my initial thought was to use remote symbol servers. Remote symbol servers is a feature of debuggers. When you debug some program, you can set the path to a remote symbol server either by HTTP or SMB. And then the debugger would fetch symbol files from that server throughout the debugging session. The most common PDB symbol server in the world is probably Microsoft Symbol Server, which hosts the binaries, the PDB files for most binaries ever shipped with Windows. But many software development groups have their own internal PDB server where they push symbols to their software throughout the CI/CD process. And my thought was that given the attacker controls or man in the middle the connection between the victim machine and that symbol server, he could serve arbitrary PDBs and crash or exploit the victim's debugger remotely. This is a screenshot showing that actually works. I was debugging Notepad with that WinDBG below, setting the SYM path to a remote server by SMB, and then loading one of the PDB files WinAFL discovered. And as you can see, that debugger itself crashed with an access violation in the PDB parsing code. So this shows that the attack surface can work. And at this point, and this was about a year ago, I decided to report that issue to Microsoft MSRC. I chose one of the PDB files that seemed more likely to be exploited and reported that info along with the attack surface. And Microsoft replied about a month later saying that this bug doesn't meet the bar for security servicing, and they closed that case. My understanding from their reply is that the reason why is that they thought the attack surface is too complex or too unlikely. And as you can see, they said that the attacker would have to control the symbol servers or man in the middle of the connection, and the victim would have to manually load a PDB file from that server. And they did say they're likely going to fix that in some future product release, but no CVE is going to be assigned. So at this point, I left this project aside for a while and didn't report the other bugs to Microsoft because they didn't seem to be interested. But then, following a conversation with a friend of mine, I realized that they rejected this because of the attack surface. So maybe I should look for other attack surfaces. Maybe there are other flows or other components in Windows that parse PDB files. And it doesn't necessarily have to be a remote code execution flow. Maybe there is some privileged service or process that loads PDB files from disk that I can exploit for elevating privileges on a local machine. And the way I approached this was very simple. I started by doing a text search for the string debug help in all binaries under the C Windows directory. And that search yielded about 30 different executables, and 2 of them immediately caught my attention. Those are faultrap.dll and where.dll. And the reason why is they are part of the Windows error reporting suite, which is a component of Windows which I already researched into quite depth in the last 2 years, discovering over 15 different vulnerabilities in it. And you can check out my Blue Hat talk from last year if you're interested in that topic. So let me do a quick recap of how Windows error reporting works. Windows error reporting purpose is to collect information regarding crashes or hangs in a Windows endpoint and report them to Microsoft Cloud for further diagnostics. And the way it works is that each time a process crashes, from its exception handler, it talks through ALPC to WhereIsVC, the Windows error reporting service, pretty much saying, hey, WhereIsVC, I am about to crash. WhereIsVC in turn will end up calling the function createProcessAsUser to spawn a new instance of a worker process called wherefault.exe. Wherefault.exe in turn would actually read the data from that crashing process, producing that crash report, and report it to Microsoft. Now, despite the fact that WhereIsVC is the one creating wherefault, it creates it as a child process of that crashing process rather than of its own. I reverse engineered wherefault to see how it used DbgHelp, and I found out that it is being used to parse the stack trace of the crashing thread in that crashing process, and then it produces a stack trace hash based on it and adds it on top of the error report. And I guess the reason why is that Microsoft are getting millions of crashes a day, and they want to be able to group those crashes by stack trace. So that's the actual pseudocode from wherefault showing the usage of DbgHelp. And it is used in a function called util_get_stacktrace, which gets the process ID and thread ID of the crashing process. It then opens that process with all access and passes the handle to that process onto the DbgHelp function SymInitialize. The purpose of SymInitialize is to initialize the symbols handler for that specific crashing process. Later on, wherefault will end up calling the function stackWalk in a loop, obtaining one stack frame at a time from that crashing process. Now, one thing we have to more carefully examine is the third argument to SymInitialize, which is a Boolean flag called finvade process. Finvade process is set to true by where fault, and that means that at that time, siminitialize would try to load the PDB file for every loaded module or DLL in that crushing process. And you can see it here in that process monitor snippet where I crushed Notepad, and the where fault handling that crush tried to load the PDB file for Notepad, NTDLL, kernel32, kernel base, and it would do that for every module loaded into Notepad. So now that we know that where fault parse PDB files, let's discuss what permissions or privileges where fault runs as. And where fault usually runs with the same permissions as of the crushing process. And this makes sense because it has to open that process and read its memory in order to produce the crush report. But there's one exception for that, which I was already familiar with at that point because I discovered another vulnerability in that flow. And if the crushing process runs under the low integrity level, then the where fault handling that crush runs under medium integrity level, which is more privileged. So for non-Windows folks, let's discuss what are integrity levels. And integrity levels is a feature that was introduced by Microsoft at Windows Vista because they realized that most users run as local administrator accounts on their machines. And that means that if an attacker exploits a vulnerability in the context of a process running as local administrator, it completely owns that system. And Microsoft wanted to come up with some mechanism to further restrict processes or contexts that run under the same user account. This is a Process Explorer snippet from my Windows 10 machine. And as you can see, Explorer.exe, the Windows shell, for instance, runs under medium integrity under my account, as opposed to Process Explorer itself, which runs under high integrity level, which is more privileged. Now, the low integrity is usually used for application sandboxing. For instance, the Internet Explorer renderer processes run under low integrity level. Those processes render all the HTML and JavaScript provided by remote HTTP servers, which is a logic that's very much likely to have security vulnerabilities in. So Microsoft wanted to restrict those processes, and if an attacker exploits a vulnerability in that context, it will only run at low integrity and be limited with what we can do to that system. So browser exploit chains nowadays usually chain a renderer RCE exploit followed by another bug to escape the sandbox. And that's the game plan for our attack surface. This is exactly what I'm going to try to achieve: elevate privileges from low integrity to medium integrity. And I'd assume I'll already run code at native level on low integrity on the system that I'm exploiting. So from that low integrity process, I'd write the malformed PDB file I discovered to disk. Then I crush my own process, which will spawn where fault at medium integrity to handle that crush. And hopefully that instance of where fault would load the PDB file from disk, and the PDB parsing bug would be triggered in its context. And if I exploit that, I could elevate privileges. So to do so, there's one problem I have to solve. I cannot write to most paths on disk as low integrity. And this is one of the basic restrictions that low integrity level poses. So there are a few directories that are writable by intention, like the appdata local directory under the users directory. So I can write my malformed PDB files to that directory. But how can I get where fault to load it from there? And apparently there's a very easy workaround for that. When you compile some binary, the compiler puts the path to the PDB file at the time of compilation onto the PE executable header of that binary. And if you later debug your code on the same machine you compiled it, then the debugger would know where to fetch that PDB file from. And apparently DbgHelp honors that value, which means that given that I can run my own executable at low integrity level, I could set the PDB file path on that PE header onto the appdata local directory, and where fault would load the PDB file from there. And you can see it here in this snippet. At the Process Explorer snippet above, I ran self-crash at low integrity, and when it crashed, it spawned where fault on medium integrity to handle that crash. And the WinDBG snip below is debugging that instance of where fault. And as you can see, where fault crashed with an access violation in the PDB parsing code at medium integrity, which shows that this attack surface in fact works and can be used to elevate privileges. So now let's start the second part of this talk, where I discussed into depth one of the PDB parsing bugs in DbgHelp and how it can be exploited in that context. So this is a very simplified pseudocode of the bug in DbgHelp. First, some integer index value is read directly from that PDB file. An attacker has full control over that value. Then there are certain checks on that index, which we'll discuss later on. And that index is used to select an object from an array of objects that's already been initialized at that point. But that index value is not used as is, but the value 1 is subtracted from that index value. And the reason why is that this is a 1-based index onto the array, while array access in C and C++ is a 0-based access. So DbgHelp had to correlate the two. Finally, on that selected object, a virtual function call is being called. Now, Microsoft did have a few checks on that index value to make sure that it doesn't go out of bound of the array and its value is not too high or too low. But they were missing a check for the value of 0. And if that index value is 0, the 1 is still subtracted from that index, and the -1 cell of the array is going to be selected. And this results in a type confusion vulnerability, confusing whatever data we have just prior to that array with an object pointer. So what's on the -1 index of that array? I found out that that array itself is allocated on the Windows heap. And prior to every heap allocation, you have the heap header, which describes some metadata regarding that specific allocation. And that means that the only primitive that this bug allows is to type confuse the heap header with an object pointer. So I decided to take a look at what the heap header looks like. And it is an 8 bytes header prior to every heap allocation. And given that I tried to exploit that vulnerability in the context of a 32-bit process, which I promise I will later tell you why, this means that I'm going to treat the lower part, the lower D word or 4 bytes of that header as an object pointer. So the heap entry structure describes the actual struct of that heap header. And as you can see, those last 4 byte meaning is the previous size, segment offset, and unused bytes part of that heap allocation. And my initial thought was that maybe I can control or predict those values somehow, because I do have a certain degree of control over the objects array. But then I found out that Windows has a feature that's called heap encoding that prevents me from doing so. Heap encoding is a security cookie-like feature that aims to prevent exploitation of heap overrun vulnerabilities. And the way it works is that the allocator encodes or XORs the value of the heap headers in memory with a random XOR key. And what that poses on attackers, imagine in the past they had a primitive to overflow the heap. So what they used to do is to overwrite the adjacent or next heap header for the next chunk and set it to arbitrary values. And there were pretty good exploitation primitives you could construct with that. But given that heap encoding feature, unless they leak that random key, they cannot do so. So the key itself is an 8 bytes key that's generated per heap at runtime in the ntdll rtlp create encoding function. But I found out that there's a weakness in its implementation. And part of that key is always set to zeros. More specifically, the higher 2 bytes of the lower part of that header are set to 0. And if you recall, if you XOR something with 0, then its value would remain clear text. And that means that Microsoft wanted to keep those 2 bytes of their original content and not encoded. And I'm not really sure why. It could be for some compatibility reason or for some optimization. So given that, is the heap header value predictable? Now imagine this is the content of that heap header. So the fake object pointer is going to be treated as its lower part. And the most significant byte in that fake pointer meaning is the unused bytes part of that heap buffer. And unused bytes meaning is the difference between the size the user asked for when he allocated that heap chunk and the size of buffer he actually got. Because there might be a difference between the two depending on how the allocator manages the heap. And that value remains of clear text. And I found out that for object array, which is a very small allocation for my test case, it only consists 3 pointers or 12 bytes in size, then the unused bytes part of that header is predictable. And most of the times will be equal to the value of 18. And this means that despite the fact I cannot fully predict the content of that fake object pointer, I can tell for sure that it would only point to a low user mode address. And as you'll see later on, this is sufficient for me to exploit this bug. Now what I'm trying to achieve here is to set the index value to 0, which would trigger the type confusion vulnerability. And then because a virtual function called is called upon that buffer, upon that object, that fake object pointer, then this means that that value is going to be dereferenced twice to obtain the address of that virtual function. And that address is likely not even allocated in the context of where fault. So if, as an attacker, I'd be able to allocate it and control its content, this means I'd be able to hijack the execution flow and trigger a primitive to call any absolute address I want in the context of where fault. And to do that, I've told you before, why would I be exploiting this bug in the context of 32-bit? And I found out that if a 32-bit executable crashes, then the where's VC that spawns where fault for that crash handling would spawn the 32-bit version of where fault. And that makes exploitation of this bug much easier because it is easier to spray the memory of a 32-bit address space versus to 64-bit, which is much larger. And also the allocators are way more predictable in their 32-bit version. So how exactly would I spray the memory? I had to come up with a primitive that allows me to alter where fault's address space from that crashing process running at low integrity. I obviously cannot write to its memory directly because I run at a lower integrity level. And if you recall, I told you before that syminitialize loads the PDB files for all loaded modules in that crashing process. So I decided to split my exploit functionality into 2 PDB files. The first one would spray the address space of where fault, and the second one would trigger the vulnerability in the context of where fault. And the reason why I chose to do so is that I have a lot of constraints on the PDB file that triggers the vulnerability. Its file format has to be in a certain way. And I didn't want to solve those constraints along with the ability to spray the memory of where fault from that same PDB file. So this is why I split that functionality, and I had to come up with a spray primitive from the first PDB. So my initial attempt was to create a very large PDB file with some repeated pattern that I can look up in where fault's memory. And I found out that DbgHelp maps that entire PDB file into memory regardless of its size using the map view of file API. And map view of file maps memory at very predictable locations. In 32-bit, it would try to allocate the topmost option with 64K bits alignment. So that's quite predictable, and that's pretty good from my spray primitive. And I found out that DbgHelp doesn't unmap that PDB file from memory up until syminitialize exits, even if the content of that PDB file is completely invalid and not a PDB file at all. So this is really good for me because it means that by the time I trigger the vulnerability, and the second PDB file is loaded, the sprayed memory of the first PDB file remains in place, which I can count off. So how exactly is my exploit going to look like? I'd start by running my code at low integrity, and then I write two PDB files onto the disk to the appdata local load directory, spray.pdb and trigger.pdb. Then I'd crash my own process at low integrity, which would spawn an instance of where-fault at medium integrity to handle that crash. Now the address space of where-fault at that point is going to be quite clean because it is a newly created process. And then it would call siminitialize with a handle from my own crashing process at low integrity. And I would set it up in such a way that it would first load spray.pdb and then would load trigger.pdb. And I can control that because the PDBs are loaded by the order in the peb LDR loaded modules list. So spray.pdb file would be first read and mapped into memory, which would allocate a very large portion of the user mode address space of where-fault with content that, as an attacker, I fully control. Then trigger.pdb file is going to be mapped into memory, and that would trigger the PDB parsing vulnerability in the context of where-fault, treating the heap header as an object pointer. And hopefully that pointer, being pointing to a very low user mode address, is going to point somewhere onto my spray PDB file buffer. And this means that I would have full control over the content of that object, and I'd be able to hijack the execution flow and call any absolute address I want in the context of where-fault. And this is a WinDBG snippet debugging where-fault itself at that state, proving that I can call any address I want. As you can see, the ESI register points to the 0E0E0E0E address, and I could set it to any arbitrary address I'd want at that point, which means that I could hijack the flow. But the next question would be, where should I call to? Because my goal is to be able to execute arbitrary code at the context of where-fault. And if you closely examined the slide before, you've probably seen that CFG, or Control Flow Integrity, which is a mitigation that Microsoft added at Windows 8, is enabled on where-fault. And CFG is a control flow integrity mitigation that aims to prevent ROP and code reuse attacks. And the way it works is that the compiler instruments every indirect call or jump and add a call to a stub in NTDLL, which verifies that the call target was in fact supposed to be called indirectly. And the PE itself manages all the locations that are supposed to be called in directory, and the loader works with that list. So I cannot just jump to a ROP chain and pivot the stack as I used to do before with exploits prior to CFG. But I found out that kernel32 load library is a valid CFG target at that context. And this means I can simply call it. And load library is a function that allows you to load a DLL dynamically into the process. So all I have to do is write another file, a DLL file, into the appdata local load directory, then have load library load it and run my payload from its entry point. Now, ASLR is not really an issue here. And what I mean by that is that I have to find the address of load library at runtime and put it onto my spray PDB file. But DLLs are loaded at the same base address at Windows regardless of integrity level. And this means that I can simply fetch the address of load library at runtime from my low integrity process and then build my spray buffer dynamically based on that address and put it onto my PDB file. Now, the last thing I have to take care about is how to control the argument to load library, because it is the path of the DLL that's about to be loaded. And there's a different calling convention between the original virtual function call and that call to load library, which means that I don't control the argument pushed onto the stack. But I found a workaround for that. I found a gadget function in DbgHelp itself, which is a valid call target. And that function accepts one argument as the dis pointer, which I do control. And it reads some buffer from that object and pushes it back onto the stack. Then it also reads another function pointer from that same object and calls it in directory, again with CFG enabled. So all I had to do is to chain the two. I'd have my exploit call this gadget function, which reorders the arguments, and then it would call load library for me. And this is a demo showing that actually works. I start by running CMD as low integrity level, which I'll show you by the output of the UMI command. Then I go to the appdata localhost directory and run my exploit code from there. As you can see, that spawned another instance of CMD, but this time it runs under medium integrity level, which shows that I was able to elevate privileges from low to medium. So now, after we've seen the first demo for this talk, I wanted to make things a little bit harder and use that same exploit to escape the Internet Explorer Enhanced Protected Mode sandbox. Now, Enhanced Protected Mode is a feature of Internet Explorer that is not enabled by default. You have to check it through Internet Explorer settings. And if you do so, then the renderer processes run under app container, which is an even more strict environment than the low integrity process. But I don't have the time to go into the exact details of how app container works, so I won't discuss it right now. But what you need to know for this exploit is that if that renderer process of Internet Explorer crashes under app container, the where fault handling that crash would also run under medium integrity level. So my plan was to run my code at that renderer process, crash it, and exploit the bug the same way. But I found out that the PDB bug behaves differently in that context, and that the fake object pointer or lower part of the heap entry points to a kernel mode address rather than a very low user mode address. And after some debugging, I figure out why. In case Internet Explorer crashes, that objects array is allocated on the low fragmentation heap, which is the optimized heap implementation of Windows. And the heap entry structure on the LFH looks a little bit different, and that address, because of that, ends up being a kernel mode address, which I obviously cannot allocate, and dereferencing it will result in an access violation. And the reason why it happens is that where fault reads a lot of memory from that crashing process. And from my own process that didn't do much work at the time, the LFH was not kicked in, because the LFH kicks in only after a certain number of allocations at a specific size are done, and then it would put that bucket of buffers onto the LFH. So for Internet Explorer, that's a very busy process. That's not the case, and this is why that bug behaved differently. So my original thought was that maybe I'd exploit another PDB parsing bug to exploit the Enhanced Protected Mode sandbox. But then I found out that I am allowed to create child processes from Internet Explorer sandbox. They would still run under app container, but this is sufficient for me. And all I had to do was to chain a proxy process here in the middle. Internet Explorer would run it, and then that process would crash, and I just simply trigger the bug that same way. And this is the final demo for this talk, showing this actually works. I'll be running Internet Explorer and show you that the renderer process runs under an app container. Then I would inject my code into that app container process, mimicking an attacker exploiting a vulnerability in the context of that renderer. And as you can see, another instance of CMD was spawned again at medium integrity level, showing I was able to escape the Internet Explorer Enhanced Protected Mode sandbox and run code at medium level. So after writing those POCs, I reported the bug to Microsoft again with that new attack surface details, and now they agreed that it does meet the bar for security servicing and that it should be fixed. And their fix was quite simple. It was shipped a few months later, and all they did is to make where fault no longer parse PDB files from disk. And the way they did that is to call the function simSetExtended option, which tweaks the way simInitialize works. And they used an undocumented argument of the value 3, which reverse engineering DbgHelp I found out that simply means do not load PDB files. And that basically killed the attack surface of having Warefault parse malformed PDBs. Now, that would be all for this talk. And a few takeaways I want you to take from here is, first of all, that fuzzing is a very efficient tool to find vulnerabilities in the right targets. And that's something that every security researcher should have in his tool belt. Next, my exploit worked on the latest Windows 10 at the time, despite all mitigations. And the main reason it was quite easy to exploit was that I could trigger the bug in the context of the 32-bit compatibility layer, which is just not as strongly mitigated as 64-bit. Next, if you have one bug, there might be multiple attack surfaces into exploiting it, especially if that bug is in some shared library. And finally, the fix by Microsoft didn't fix the DbgHelp bug, and it exists in code until today. They only kill the attack surface. So maybe you guys can find other attack surfaces into that parser and trigger that bug on your own. Thank you very much. That'd be all. If you have any questions, now would be a good time to ask. And otherwise, you can always ping me on Twitter. Thank you very much.